Let's check out the security room near the cursed castle at Sketchyland to understand how insulin, glucagon, and epinephrine regulate the synthesis and degradation of glycogen. The security team not only monitors any suspicious activity happening at Sugar Street, but they also store some vague documents in the control room. Last week, there was some unconfirmed rumor circulating around about some kind of raid, and people were saying that they needed to shred some files, but nothing really happened, so probably nothing to worry about. Anyways, looks like we've got some action on the TV to the left. Up top is a ghoul making some cotton candy. Recall that she's glycogen synthase, which catalyzes the rate-limiting step during glycogen synthesis. Down below is a guy with a glowing necklace powered by a P battery. He's glycogen phosphorylase, the enzyme that catalyzes the rate-limiting step during glycogen degradation. Hey man, stop feeding the ducks! As you'll see shortly, the hormones insulin, glucagon, and epinephrine act on these enzymes to control how much glycogen we make or break down. As a reminder, insulin is an anabolic hormone that facilitates the absorption of glucose from blood to skeletal muscle, adipose tissue, and the liver. Insulin promotes the synthesis of proteins, triglycerides, nucleic acids, and glycogen. Our recurring inside welcome mat will remind you of insulin. And it looks like someone left a little glycogen cotton candy there. Wonder who that was. Let's dive further and look at what's going on at a cellular level. As you can see from this diagram, insulin binds to the insulin receptor on hepatocytes and skeletal muscle cells. The insulin receptor is a part of the large class of tyrosine kinase transmembrane receptors and is made up of 2 alpha and 2 beta subunits. The alpha subunits are present outside of the cell and bind insulin, while the beta subunits are intracellular and contain intrinsic tyrosine kinase domains. Insulin binding to the receptor causes the subunits to dimerize while activating tyrosine kinase. Oh, we forgot to mention, earlier today they found a lost tyke near the acid mines of the Odd West ride, but don't worry, we got a hold of Mom and she's on her way. This kind-hearted tyke is tyrosine kinase. And notice how he's sitting on the inside mat to remind you that insulin activates tyrosine kinase. Okay, not really. I think he just finds the mat comfy. Tyrosine kinase then starts autophosphorylating a bunch of tyrosine residues on the inner part of the insulin receptor. You get a phosphate, and you get a phosphate, and you get a phosphate. Tyrosine kinase also activates insulin receptor substrate 1, or IRS1, protein through phosphorylation. The worker filling out IRS paperwork is IRS1. You should know that IRS1 activates protein phosphatase via an intermediate called PI3K. Dot your I's and cross your T's. The tax man is here and nothing in life is more certain than death and taxes. And I'll tell you what, our friend from the park doesn't seem like he's happy about what he's doing right now. Protein phosphatase has 2 important jobs. 1, it directly activates glycogen synthase by removing a phosphate group. The Fed wants access to video files of the ghoul making cotton candy, but they're locked by a firewall. In order to access those files, the P battery needs to be removed from the firewall. It's very high-tech. And 2, protein phosphatase inhibits glycogen phosphorylase kinase, the enzyme that normally activates glycogen phosphorylase, by removing a phosphate group. Watch the Fed grab another P battery from another worker, who, by the way, is glycogen phosphorylase kinase. Ultimately, this inhibits glycogenolysis. So to recap, insulin promotes glycogenesis and inhibits glycogenolysis. Okay, besides insulin, cortisol and glucose-6-phosphate, or G6P, also activate glycogen synthase. Pushing this moon face button will play the video of our ghoulish friend. The moon face is our recurring symbol for corticosteroids. Interestingly enough, cortisol promotes glycogen synthesis in the liver even though it has a catabolic effect in peripheral tissues. Cortisol increases insulin resistance in peripheral tissues, which therefore decreases peripheral glucose uptake and raises blood glucose levels. As a result, insulin acts on the liver to direct the excess glucose into making glycogen. What about G6P? Well, high G6P inside cells means we have plenty of glucose available, and therefore can store it as glycogen. Let's move on to glucagon. As you probably already know, glucagon is basically the opposite of insulin. Glucagon is active if you haven't eaten anything all day, and it promotes gluconeogenesis and glycogenolysis in the liver. The glucagon sugar-free candies next to a liver-shaped tray with empty cotton candy sticks will help you remember that glucagon makes glycogen go away. Bye, Felicia! During a fast, low blood glucose stimulates the release of glucagon from the pancreatic alpha cells. Glucagon binds to the glucagon receptor present on hepatocytes. The glucagon receptor belongs to the large class of G-protein coupled transmembrane proteins. Binding to the receptor ultimately leads to activation of adenylate cyclase, which cleaves ATP to cyclic AMP. Cyclic AMP will then activate protein kinase A. The Camp Sketchyland poster up on the wall above the sugar-free packets will help you remember that glucagon results in adenylate cyclase, cyclic AMP, and protein kinase A going up. Protein kinase A has several functions. First, it inactivates glycogen synthase by phosphorylation. See the TV and firewall on the right? When the P battery is in place, the Ghoul video doesn't play. Second, protein kinase A activates glycogen phosphorylase kinase by phosphorylation. Remember that guy earlier getting harassed by the Fed? Yeah, he's glycogen phosphorylase kinase, and he loves PKA so much that he's wearing it as a shirt. It's just what gets him going in the morning. Okay, this one's a tongue twister. Ready? Through phosphorylation, glycogen phosphorylase kinase activates glycogen phosphorylase, which is the enzyme that starts the breakdown of glycogen. Now, if you're anything like me, which is to say a cat-loving nerd with a warped sense of humor, then you never want to hear the word phosphorylate ever again. Well, bad news? We still have to add some phosphate groups. Good news, I'm not going to say it 3 times in one sentence again. Let's switch gears now and talk about epinephrine. Epinephrine is produced in response to stress. One of the main functions of epinephrine is mobilizing glucose stores so it can be used for energy. Epinephrine promotes glycogenolysis in the liver and skeletal muscle. Let this ad for epic times remind you of epinephrine and how it's important with regards to breaking down glycogen. Epinephrine activates the same things as glucagon, but it binds to beta receptors on hepatocytes and skeletal muscle, which is represented by the beta-shaped antenna just underneath the Camp Sketchyland poster. Protein kinase A also activates glycogen phosphorylase kinase, resulting in activation of glycogen phosphorylase and subsequently, glycogenolysis. Epinephrine can also bind to alpha receptors on hepatocytes. The alpha receptor is another G-protein coupled transmembrane protein, but unlike the glucagon and beta receptor, binding results in activation of a different signal transduction pathway. Epinephrine binding to the receptor site activates another G-protein, but this time, instead of activating adenylate cyclase, it turns on phospholipase C, or PLC. PLC turns PIP2 to IP3 and DAG. The picture-in-picture, or PIP, of 2 kids in this picture frame is PIP2, and the 3 dogs, DAGs, will help you remember IP3 and DAG. IP3 diffuses into the cytosol and binds to the IP3 receptor on the endoplasmic reticulum, which results in the release of calcium into the cytosol. Yeah, who's your good puppy? Playing catch with your bone. Calcium will then bind to calmodulin to form the calcium-calmodulin complex, which activates glycogen phosphorylase kinase. Glycogen phosphorylase kinase will subsequently activate glycogen phosphorylase, and we break down glycogen once more. One last thing I want to say. AMP will also activate glycogen phosphorylase. Low AMP means we don't have enough energy available inside cells because we've used up the ATP. Therefore, we need to generate more glucose by breaking down glycogen so we can start making more ATP. Alright, let's quickly wrap up before the IRS starts looking for me. Glycogen synthase is the rate-limiting enzyme during glycogen synthesis, while glycogen phosphorylase is the rate-limiting enzyme during glycogenolysis. Through signal transduction pathways, the hormones insulin, glucagon, and epinephrine target these enzymes. Insulin specifically promotes glycogen synthesis by binding to insulin receptors on hepatocytes and skeletal muscle, resulting in activation of tyrosine kinase, IRS1, PI3K, and protein phosphatase. Protein phosphatase removes a phosphate group from glycogen phosphorylase kinase and glycogen synthase, allowing glycogen synthase to be active. In contrast, glucagon promotes glycogenolysis by binding to glucagon receptors on hepatocytes, resulting in activation of adenylate cyclase, cyclic AMP, and protein kinase A. Protein kinase A phosphorylates glycogen synthase to shut it off, while also phosphorylating glycogen phosphorylase kinase to turn on glycogen phosphorylase. Epinephrine can activate 2 different signal transduction pathways to promote glycogenolysis. Binding to beta receptors on hepatocytes and skeletal muscle activates the same signal pathway like glucagon. Alternatively, epinephrine binds to alpha receptors on hepatocytes, resulting in activation of phospholipase C, or PLC, which cleaves PIP2 to IP3 and DAG. This will eventually result in the release of calcium into the cytosol, activation of glycogen phosphorylase kinase, and glycogen phosphorylase.